give you the exact form as it's written in our book. There's a minus sign, depending on the way the problem is initially presented, that is important. The exact form, as our book has it, is dy dt is equal to g of t comma y over f of t comma y if the partial derivative with respect to y of, no, don't write that. If the partial derivative with respect to t of f of t comma y is equal to, here's the part that might surprise you, and I'll show you where it comes from, minus the partial derivative with respect to y of g of t comma y. Where does that minus come from? I'll show you where the minus comes from. So separable equations are also exact equations. And so that's where our author is presenting these two in the same book or in the same section. And so what the goal is remember when this was just g of t at f of y, that was our separable equation as we just solved it in the last hour. And so, but when they're exact, you can't quite use the same strategy. You have to use, you can't even do the problem unless you can figure out if this is true. And this pattern, this minus, comes from this. So if you start with dy dt, this is where it comes from, is equal to g of t comma y over f of t comma y. You multiply by f, and so you have f of t comma y dy dt equals g of t comma y. The minus comes from this, f of t comma y dy dt minus g of t comma y equals 0. And then one more thing is done. We've been multiplying the differentials. So if you multiply them out one more time, you would write it as f of t comma y dy minus g of t comma y dt equals 0. And look at this. What did we say? We said, or look, if you look over there, our function f was originally, it was differentiated with respect to y. Our function g was originally differentiated with respect to t. And so if you look at it in this form, you can see which one has had which derivatives. And so it's easy to remember when you take the test, you're like, oh, the f has already been derived with respect to y, so I need to check it with t. G has already been dealt with respect to t, so I need to check it with respect to y. So let's try. Let's try. I'm going to do a problem out of your book. It's problem number 13. B, 13B. And it says what we're going to do is we're going to solve dy dt equals minus 1 plus y e to the ty over 2y plus t e to the ty. If that doesn't look daunting, I don't know what would intimidate you. And when I looked at that, I thought I should try a different one instead. No, let's do it. So let's try this. Okay, so I know this is a lot of ideas. Let's try to put it together. First step is none of this matters if it's not exact. So the first thing we need to do is 1, check for exactness. Check for exactness. Or just, I'm not sure. Would it be exact or exactness? Yeah.
So, I mean, let's just start with separate. Right? If you could separate y and t, it works, right? That's just the difference.
Correct.
And so now we're doing that. So for some reason you can't separate them.
Yes, I'm back.
Okay.
They're stuck.
Yes. And that means we still can do it only if. I'm still confused as to what actually happened on these two sets of words. But if those whatever the heck is true, then we can do it.
Yes. You got it. See, you got it.
I understand that, but
Nice. Right. Yeah. So that's if all that holds, it ended over here, then we can still solve this problem that can't be separated. But it's still written in a separable form, or it looks separable. Well, because remember, we said separable. We said separable was this. It was dy dt was g of t f. That's why you're seeing the similarity between.
can't do this one whole.
No. Yeah, because you can't separate it into functions only of t and functions only of y. So here's how we do this. Check for first. We have to just see if this is even going to work. So, let's yeah.
What does it mean to be exact?
This.
Why is it called exact?
I don't know. Because they work out to be exactly the same, I suppose. I don't know who named it. I don't, but my understanding is they're exact if this condition holds. This is an exact differential equation. Check for exact. So let's do this. Let's let, just so everyone's, we're going to use our same notation. We're going to have g of t comma y as our numerator. And just so we don't mess around with this, let's put that minus sign into the numerator. So we're going to write g of ty is minus 1 minus y e to the ty. So, now we're going to put an additional minus in here. Minus the partial. So g, in order to check for exact, do we differentiate with respect to t or with respect to y? Why? Why not? Just out of desperation, we'll just try y. So minus the partial with respect to y. I'll just put it in parentheses. Minus 1 minus y y equals. Where is it? I'm going to put that minus and then we'll distribute it later. Oh, this, I can start us off on the right foot. The derivative of -1 doesn't matter if it's y or that's 0. I'm gonna put that placeholder down. Minus, now, well, derivative of the first is 1, so minus, we have 1 e to the ty plus, then we're going to have y times the derivative of the second. Well, that's going to be e to the ty. Y is the variable, so it's going to be the derivative of ty becomes times the. Did I do that correctly? I hope so. Good. Okay. So let's clean that up and let's write it in its final form. Let's distribute the minus, those cancel. So my final answer is e to the ty plus ty e to the ty. E to the ty